recording. So parts of the spherical mirror. Whether concave or convex. Whether concave or convex, a mirror is drawn to have a very small aperture. The aperture of the mirror is not so we don't draw a mirror to look like a basin or a tree. No. In fact, theoretically, the mirrors are thin mirrors, as if it's a straight line. They are actually thin mirrors, slightly curved. Okay, slightly curved, but for explanation purposes, we draw it to look like the oval. Now, the size or the width of the mirror is known as the aperture of the mirror. So if concave, the back of it is coated. So AB, which is the width, is technically called as the aperture. So AB is the aperture of the mirror. Then the center or the middle of the mirror is given a special name. The center of the mirror, represented by the letter P, is known as the pole. So the pole is actually the center of the mirror. Then for ray diagram purposes, there is an imaginary line, horizontal line, passing through the center or the pole of the mirror, which divides the mirror into two parts. So this imaginary horizontal line, which passes through the pole, okay, dividing the mirror into two equal parts. This point or this line is known as the principal axis. So let's assume it starts from O. The line OP. The line OP is known as the principal axis. So OP is the principal axis of the mirror. And this is an imaginary line. Imaginary because, in fact, when you pick a mirror, you will never see this line. Okay. It is indicated for ray diagram purposes. It is indicated for ray diagram purposes. Please let me take a shot of attendance and drop it into the group. You are only 16, which is not so encouraging. Okay, so give me a minute, I'm coming. So the principal axis is an imaginary, okay, line, horizontal line dividing the mirror into two equal parts. And please, all these parts applies to both concave and then convex, all spherical mirrors. But I'm just using the concave mirror for analysis. Okay, then there is another point. There is another point on the principal axis where all paraaxial rays, I'll explain the terms, paraaxial. So this ray is such that all rays that are close and parallel to the principal axis, all rays that are close and parallel to the principal axis, rays must always be indicated with an arrow so you don't overlook your arrow. Okay, so paraaxial rays, paraaxial rays are rays that are close and parallel to the principal axis. These are rays that are close and parallel to the principal axis. So its opposite rays are termed as marginal rays. Marginal rays. Marginal rays are not close to the principal axis. They are parallel, all right. But when the ray is incidented on the mirror and the rays are far away from the principal axis, they are termed as marginal rays. But all rays that are close, very, very close, and then parallel to the principal axis are. Now, when rays are so parallel and close to the principal axis, what happens is that after reflection, after reflected from or by the mirror, they all intersect at a point. They all intersect at a point. The condition is that all the rays must be close and parallel to the principal axis, meaning they must be paraaxial to do that. If they are not paraaxial, they wouldn't meet at a point after reflection. So we have a point on the principal axis where all paraaxial rays converge at after reflection. So all these are reflected, reflect a small arrow. And the point where all paraaxial rays converge after reflection is known as the principal focus or the focal point, represented by the letter capital F. So capital F is known as the focal a principal focus. Or focal point. Or focal point. So, if you are asked what the principal focus or focal point of a concave mirror is, it is a point on the principal axis where all paraxial rays converge after reflection. What did I say? What is the principal focus of a concave mirror? Yes, class, what's the principal focus of a concave mirror? Hey, somebody to re-echo that for us.
It is the point where all paraxial rays converge
So it
after
is,
reflection.
you are right, but it is a point on what or at where? It is a point on the principal axis. It's a point on the principal axis OP, where all paraxial rays converge after reflection. Or instead of using paraxial rays, you can say that it is a point on the principal axis where all rays that are close and parallel to the principal axis converge after reflection. Okay. Now, the distance between the pole of the mirror and then the principal focus, this distance is known as the focal length, F. So, know the difference. Capital F is a point on the principal axis where all paraxial rays converge, represented by capital F. Then, small letter f is the distance or the length between the pole of the mirror and then the principal focus. So small letter f is known as focal length. So principal focus is a point on the principal axis where all paraxial rays converge after reflection. Then the focal length f is the distance between the the pole of the mirror and the principal focus or the focal point. Okay, let's look at the principal focus and then the focal length of convex mirror too. This is for concave. Let's look at how that of convex mirror also plays out, so that we distinguish between them. Convex mirror, we expect the mirror to curve, the reflecting surface to curve inwardly. Technically, mirrors are drawn to have small aperture. They are thin mirrors. So let's assume this is the middle, meaning the pole is here. Then a horizontal line dividing the mirror into two. So this line, PO, is known as the principal axis. In fact, all measurements are taken from the pole. So when you are measuring the focal length, blah, 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 all measurements are taken from the pole. Okay. And this is like this because, you see, for concave mirror, we always place the object at the reflecting surface. So object will be put here, incident and reflect. Object will be put here. So all measurements, the reason for which the convex mirror has this line going from left to right. This is from right. This is from right to left. Okay. And then this is right to left, left to right. So note the difference. Okay. Now let's incident paraxial rays to this mirror. Rays that are close and parallel to the principal axis. Just few lines to represent practically. Practically these lines are far away, but let's use this for theoretical purposes. So about 4 lines. They are incidenting on the mirror. And we are assuming that these lines are paraxial. How does this mirror relate to incident beam of light? How does the mirror relate to incident beam of light? Yes. Elizabeth, how does convex mirror relate or behaves to incident beam of light?
You see, it diverges them.
Thank you. So this mirror diverges incident rays, whereas this one converges incident beam. So
Recording in progress.
we are
We are
going
going to.
I'm
I'm
coming.
coming.
The usual shots. Okay. All right. So when rays incident on this, they'll all be diverged. All paraxial rays are diverged after reflection. Just few lines. So these are the reflected rays or the diverged rays. Now, you see, when I was tracing the diverged rays, I also connected the diverged rays to a point on the principal axis. This point. It's a virtual point. So the reason for which I'm using broken lines to indicate that point. So here, all diverted rays appear to be diverted from a point on the principal axis. All diverted rays appears to be diverted from a point on the principal axis. This point is known as the principal focus. So we define the principal focus of a convex mirror as a point on the principal axis where all paraaxial rays appear to be diverted from after reflection. A point on the principal axis where all diverted or reflected.
So please come again. My line was breaking, so I couldn't hear you
I'm
quite
writing.
clearly.
I'm writing on the board. So a point on the principal axis where all diverted rays appear to be diverted from after reflection. So this point on the principal axis where all diverted rays appear to be diverted from after reflection. So you see, in drawing the reflected rays, you must trace it to a point on the principal axis. And that point where all diverted rays, okay, appear to be diverted from after reflection is known as the principal focus of a concave mirror. Okay, because of this behavior, you see, this point appears, so it's a virtual situation. Because of this reason, we term the principal focus of convex mirror to be virtual, because that point is a virtual point. All diverted rays appear to be diverted from, and the distance between the pole of the mirror and then this virtual point is also termed as the focal length f. In the case of concave mirrors, the principal focus is real, meaning paraaxial rays actually converge at this point after reflection. So it is real in mirrors. All points or images formed in front of the mirror are real. All point images formed behind the mirror are virtual. Okay, so the principal focus of a concave mirror is real, whereas the principal focus of a convex mirror is virtual. Please, any question? So the question to the house, if you are not asking your own question, is that how would you define the principal focus of a spherical mirror? How would you define the principal focus of a spherical mirror? We've talked about the principal focus of concave, principal focus of convex. How would you then define the the principal focus of a spherical mirror generally? Anybody to try? Let me give it to Delix. Dela, you're also here. Delix or Dela, the DDs. Try. It's just trial, okay? Just trial. Delix, try. The principal focus of a spherical mirror. Dela, either Delix or yourself, just give it a try.
I just
Nana, okay, go ahead. Nana, go ahead.
Sorry. It is a point on the spherical mirror where parallel rays
A
meet
point on the principal focus.
on the
Principal
principal axis where parallel light rays meet.
Okay. You are to try, so thanks for trying. Who else would confidently try as Nanajua has just done? Yes, Caleb, Leslie, Leonard, Lenny.
Sir, please, the question again.
So what were you doing? The question is about what is the
My line was
principal
breaking.
what is the principal focus of a spherical mirror? How would you define the principal focus of a spherical mirror?
Well, it's a point on a spherical mirror where all reflected converged, where all reflected rays meet. And for the convex mirror, it is where all diverged rays appear to meet.
Okay, not bad. But please take note, it is this
You can also say
point.
that it is half the length.
I get what you are trying to chip in.
Okay.
So you leave that for me. You see, the principal focus is a point on the principal axis. So listen to the definition. It is just a way of combining the two. Okay. So we define the principal focus of a spherical mirror as a point on the principal axis where rays that are close and parallel to the principal axis actually meet or appear to be diverted from after reflection. I take it again. It is a point on the principal axis where all rays that are close and parallel to the principal axis, yeah, I mean paraxial rays, actually meet or appear to be diverted from after reflection. So by saying this, you are joining this and that. Okay. So a point on the principal axis where rays that are close and parallel to the principal axis actually meet or appear to be diverted from after reflection. All right. Then there is another point. There is another point. Mamia. Mommy, are you there?
Yes, please.
Angel. Eva. Roll call. I hope you're all there. Safo, are you there? Safo.
Yes, please.
Okay. There is another point. This point, I said all the points applies to both concave and convex. So when I finish, I would use the other mirror to also explain. For now, this is concave. Now there is also another point. This point on the principal axis is such that irrespective of wherever a ray can be propagated from. So this is a ray. Its direction is from up down, hitting the mirror in the direction of the marker. Okay, so the arrow shows where the ray is coming from and where the ray is incidenting. Then another ray. This ray is coming from, this is the direction, down, up. Now the condition is that if the ray incidents on the mirror at an angle equal to 90, normally, so no matter where the rays can be coming from, if the ray incidents on the mirror at an angle of 90, something special will happen. Something special will happen. What is that special thing? The moment the ray hits the mirror at 90, no matter where the ray is coming from, it will reflect along the same path. So after reflection, it will hit the same, the reflected ray takes the same path and all pass through a point or converge at a point on the principal axis. So I take it again. No matter where the ray is coming from, up or down, that is why I have used two arrows. When the ray incidents on the mirror at an angle of 90, normally the ray reflects along the same path as the incident and passes through a point on the principal axis. Passes through a point on the principal axis. This point is termed as the center of curvature. C. So we define the center of curvature of the mirror here concave. As a point on the principal axis where rays that incident on the mirror normally, please, normally here we are referring to perpendicularly, actually passes, okay, after reflection. So a point on the principal axis PO or OP where rays that incident on the mirror perpendicularly or normally passes or converge after reflection. Don't forget, even for mirrors, whether plane or curved mirrors, when a ray hits a plane mirror at 90, it reflects along the same path. So when you incident a ray and the ray is such that it hits the mirror at 90, it reflects along the same path. Okay, so here, irrespective of wherever the ray can be coming from, up or down, the moment it's incident on the mirror at an angle of 90, it will reflect along the same path as the incident and pass or converge at a point on the principal axis. And this point is termed as a center of curvature of the mirror. So we can have about 100, a lot of rays, so long as they all incident on the mirror at an angle of 90, they all reflect along the same path and then pass through a point, a common point on the principal axis, and this point is the center of curvature of the mirror. So this is a point on the principal axis where rays that incidents normally or perpendicularly passes or converge after reflection. This is a point on the principal axis where rays that incident normally or perpendicularly on the mirror passes or converge after reflection. Now the distance between the principal, the pole, all measurements are taken from the pole. So if you are measuring this distance, whether principal focus, the focal length or whatever, you have to start from the pole. The distance between the pole and then the center of curvature C is known as the radius of curvature. So the radius of curvature represented as the letter small r or capital R is the distance between the pole, of the mirror and the center of curvature. So C is the point. Center of curvature is a point, whereas R is a distance. Just as capital F is a point and small f is a distance. Please, any question? I have 32 of you. Any question?
No, sir.
Are we done writing? Now there's a
Yes, please.
special relationship between the radius of curvature R and the center of and the focal length F of every mirror, whether concave or convex. And that special relationship is that the radius of curvature R is always equal to 2 times the focal length. We can prove it. R is equal to 2F. And this relationship is very, very important. We'll be using it a lot in our discussion. So what it means is that for a particular mirror, concave, this is the pole. That horizontal distance we are terming as principal axis. If I choose X distance, all measurements are taken from the pole. So if from the pole to this point is F, the principal focus or the focal point, then I need to have the same distance measured from F to the center of curvature. So this will be C. Meaning if from the pole to F, this distance is maybe 2 centimeters, then from the pole to C, this distance must be 4. Because R is equal to 2 times F. So whatever you measure for this, twice of it must be 4 from the pole to C. And you must adhere to these rules so religiously. We'll be using it so you see the essence of this ugly equation or relation. All right. Let's look at that of convex. The center of curvature, the radius of curvature for convex mirror. Convex mirror curves outwardly. The reflecting surface curves outwardly. Mirrors have small aperture. We don't draw a mirror like a bowl or a basin. Assuming this point is the pole must always be the center of the mirror. Let's draw the principal axis. So the rays must always come from the object. Here, the object must be placed in front of the mirror. So let's imagine this to be rays coming from whichever source, but hits the mirror at 90. Once it is hitting the mirror at 90, it will reflect along the same path. So incident, reflected. So the condition is that no matter where the ray is coming from, it must incident the mirror at 90. It will incident and reflect along the same path. So this point, where rays that hit the mirror or incident on the mirror at 90 or normally passes or appear to pass or converge is the center of curvature C. This also implies that the center of curvature of a convex mirror is virtual because the rays appear to converge or pass after incidenting on the mirror at 90. Okay, so it's also a virtual point. So C, this is the explanation for the center of curvature of convex mirror, meaning that the radius of curvature, which is this distance, is also virtual because they all appear behind the mirror. This is R. So the most important thing is that the ray must hit the mirror at 90 and they will all appear to converge or pass through a point on the principal axis. We are done. And still, in mirrors as well, R is in convex mirrors, R is also equal to 2F. Any question? So that is the center of curvature and the radius of curvature of convex mirror. So Mamiya, or let me call Nana Safo. Nana, are you there?
Yes, please.
Nana, how would you explain the center of curvature to your younger brother? If you have to explain the center of curvature to your younger brother, how would you explain? Nana, I'm listening.
The center of curvature is a point on the principal axis where the rays incident on the mirror perpendicularly.
And so when the rays incident on the mirror perpendicularly, what happens? Nana, what happens?
The reflection moves in the direction of where it was incidental.
Okay,
Okay,
so you mean it reflects along the same path and passes or converge at a point on the principal axis.
Yes.
So don't forget that part. Either passes or converge at a point on the principal axis. And this is known as the center of curvature. Okay.
Yes, please.
But if you say so, you are only saying that for concave. You haven't merged the two. You only spoke for concave, not for convex. So Nana Kwame. Nana. Oh, Nana Kwame. Oh, he's asleep. Jacob or Joy, how would you explain the center of curvature to your brother of a convex mirror? How would you do that? Don't waste time, oh, please. Hey, the guys are asleep. Okay, Mamiya.
No, sir, you're not asleep. The boys are not asleep.
Okay, Caleb, thank you. Go ahead.
Sir, please. I would say that the center of curvature is of a convex mirror. That's where if we have light rays which are hitting the convex mirror at its extreme ends, where those light rays and are reflected in the same path they were
Along
incident
the
in.
same path.
And where yes,
Continue. Reflected along the
as
same
in a
path.
diagram.
Caleb, let me take over. Your line is breaking. Okay, for time's sake, let me take over. Okay, so
Mirror.
okay, your line is breaking. So all that we are saying is that for this one, when irrespective of where the light is coming from, please, that's why I've used two rays to show that the ray can come from this point or this point. And when, no matter where the rays are coming from, when they hit the mirror at 90, they will one reflect along the same path as the incident and either and appear to converge or pass, through a point on the principal axis. And this distance is this point is the center of curvature. Please, when you use appear to converge or pass, then you want to say that this point is virtual. And that does it for convex mirror. And so the center of curvature and then the radius of curvature for convex mirror, okay, are virtual points. All right. Then so that does it for the parts of the spherical mirror. We have gone through the aperture, the pole, the principal focus, the focal length, the center of curvature, and the radius of curvature of all the mirrors. Let's look at using ray diagrams to form formation of images in spherical mirrors. Formation of images in spherical mirrors. In spherical mirrors or curved mirrors. So we'll do that for each one of the mirrors, concave and convex. You recall that for plane mirrors, we also looked at formation of images in plane mirrors. Use two rules. A ray of light hitting the mirror at 90 reflect along the same path. The rays are always coming from the object. Then, so I'm assuming the object O is here. Then the other rule is that a ray of light hitting the mirror at any other angle obey the laws of reflection. But in drawing the image, because you know object distance is always equal to image distance, you need to have the same measurements. So if x centimeter, you need to have x centimeter at the other end. And that is the point where the image will be traced, the position of the image. So you don't just draw a reflected ray, but you need to trace the reflected ray to this point. So as to satisfy that object distance equals image distance. So I also need to trace this point. Let me draw this ray well. So this is the image I. And we can use two rules or rays. This is incidenting at 90 and so reflect along the same path. And this is incidenting at an angle. This distance is also object distance here, image distance V, and they must be the same. So this is for ray diagram for plane mirrors. When we come to spherical mirrors, we have its own ray diagram as well, and that is what we are going to go through from now. But it also has its rules. So let's quickly go through the rules, because we'll be using the rules or the principle for the image formation. So the rules, we have 4 of them. Rule 1, and we are doing it for concave. Concave mirror. There's the center. So principal axis. I'm assuming this is my focal length. So capital F is here. X distance as well for the center of curvature C. You don't always close your eyes to this because R is equal to 2F. Very, very important. The first rule is this. A ray of light parallel to the principal axis. A ray of light which is always parallel to the principal axis, after reflection, must pass through the principal focus. After reflection, the reflected ray must pass through the principal focus. So this is the first rule. And the rays are always coming from the objects. The rays are always coming from the object. Rule 2. The second rule is that the reverse form of this, of the first rule. Pole is here, F is here, and C is here. The second rule is that when the ray is passing through F, either it is from somewhere passing through F, or the ray is actually from F. Oh shit. So all that I'm saying is that either the ray is from F or passing through F, after incidenting on the mirror, the reflected ray must be parallel to the principal axis. Rule 2 is the reverse form of this. Look at this. When the ray is parallel to the principal axis after reflection, it must pass through F. So when the ray is parallel to the principal axis after reflection, it must pass through F. And rule 2 is that when the ray is passing through from F or passing through F after reflection, it must be parallel to the principal axis. Rule 2. Are you done drawing? Are we done? Okay, rule 3. Mamiya,
Please, can you come again with the rule 2?
Mamiya, the rule 2 is that a ray of light coming from the principal focus or passing through, this is passing through F, or when the ray is directly coming from F, after it's being reflected from the mirror, the reflected ray must be parallel to the principal axis. So just the reverse of this. Okay. Just the reverse rule of 1. Rule 3. The third rule is that a ray of light so you don't close your eyes to F, this distance, and this distance, C. A ray of light hitting the mirror at 90. When the ray is hitting the mirror at 90, you must incident and reflect along the same path and pass through a point on the principal axis. This point is the center of curvature. So the moment a ray diagram is drawn and it passes through C, then it means that the ray is incidenting on the mirror at 90. The reason for which it is passing, reflecting along the same path as the incident and passing through C. Okay, so it's just application of whatever we've said earlier. And then the final rule, rule 4, is that the rule 4 is that a ray of light hitting the pole of the mirror. Your F is here, C is here. A ray of light, whichever or wherever the ray is coming from, hitting the pole of the mirror or incidenting exactly at the pole, reflect at the same symmetry or axis. What we mean is that let's assume this angle is theta. It must reflect at the same angle, symmetry. So whatever this angle is, we need to have the same angle as the reflected ray or angle of reflection. That's what we mean by hitting, reflecting at the same symmetry. So these are the 4 rules of the game for concave mirror. A ray of light traveling parallel to the principal axis. I'm going through, Gabi. I'm going through. A ray of light parallel to the principal axis after reflection passes through the principal focus. 2. A ray of light passing through the principal focus after reflection must be parallel to the principal axis. 3. A ray of light hitting the mirror at 90 reflect along the same path and passes through the center of curvature. Then 4. A ray of light hitting the pole of the mirror. The pole is the center of the mirror. Hitting the pole reflect at the same symmetry. And here what I'm saying is that if this angle of incidence is 30 degrees, the virtual angle of reflection must also be 30. Symmetry, that's what I mean. So in using this rule, whichever angle you get here must be the same as that. So usually it must be measured so as to get accuracy. So this is it for concave mirrors. Let's look at it for its brother, convex mirror. How does the rule work? Do I clean the board? Yes. So for convex, curved inwardly, small aperture. The pole is here, the middle. Okay, so the principal axis. The virtual principal focus is here. So from the pole, So you need to measure this distance. And then the virtual center of curvature. Is that with what? You need to measure with a ruler. I'm just estimating. So when you have a ray parallel to the principal axis, a ray parallel to the principal axis, after reflection, this one diverges. So it will be the incident ray will be diverted. But the diverted ray must always appear to be coming from the principal focus. So for convex, this is rule 1. All right, class, please, if we are doing something and you don't understand, do not swallow it. You know me to be the type who wouldn't, explain when you don't understand. So you swallow it at your own peril. And don't forget, once you confidently ask, it also helps somebody. So if you are not clear with something, you don't swallow. So this one is such that when a ray of light is parallel to the principal axis, the reflected ray is diverged. But the diverted ray always appears to be diverted from a point. And that point is the principal focus or the focal point of. So for convex mirrors, this is rule 1. Rule 2 must also be the reverse of this, just as we saw in concave mirrors. Your F, your C measurement, always very important. You must measure this with rule. I am estimating because of time. We'll be applying it, and so you see how. So under this rule, if a ray appears to be passing through F, listen to the context. The ray appears to be passing through F. So I'm tracing the incident ray to the principal focus. The ray appears to be passing through F. So if it appears to be passing through F after reflection, what do you think will happen? Yes. Anyone to help out? If the ray appears to be passing through F after reflection, what do you think would happen? Plus, there is a question. Mamiya.
After reflection, the reflected ray will be parallel to the principal axis.
Exactly. It's just the reverse of whatever we are doing. So if the ray appears to be passing through F, Then after reflection, the reflected ray must go parallel to the principal axis. So it is also the reverse of this first one. The first one is such that if the ray is parallel, there's nothing wrong even extending the principal axis. We can extend it to the other side of the mirror. Okay. So in the first case, if the incident ray is parallel to the principal axis, after reflection, it must appear to be diverted from F. Then in the second rule, if the ray appears to be passing through F, after reflection, the reflected ray must go parallel to the principal axis. Okay, rule 2. Rule 3. Rule 3 has to do with the center of curvature thing. So when we start using this, you master. So let's go through it. When we start using, you see how it works out. Let me extend the principal axis more. So don't forget, for convex mirror, principal focus, center of curvature are virtual. So P, if this is F, you measure. I say you would have to measure. I am just estimating because of time. Okay. So a ray of light which incidents on the mirror at 90 must appear to pass through a point on the principal axis. And this point must be the center of curvature. So usually we don't even draw the angle. The moment it is linked to C or appears to be linked with C, it means that the ray is hitting the mirror at 90. So this is rule 3. Then the last rule is that a ray hitting the pole F is here. Accurate measurement, please. C is here. So when the ray hits the pole of the mirror, let me extend the when the ray hits the pole of the mirror, it must reflect at the same symmetry. So this is how the rules also work out in convex mirrors. Please, any question? Class, any question? Because start using them, using the rules to create images. Elizabeth,
So yeah, please, can you like say the third rule in words again?
the third rule says that a ray of light hitting the mirror at 90, incidenting the mirror at an angle of 90 degrees, incident and reflect along the same path. Incident and reflect along the same path. So this arrow shows that incident. This other arrow shows reflection along the same path. Would appear to pass through a point on the principal axis. And this point is the center of curvature C. Okay.
Yes, please. Yes, please. Thank you.
All right. So let's go through image formation, okay, using concave mirrors. As for convex mirrors, it isn't much of a problem. But for concave mirrors, different object positions would give you different images. And now you are mute yourself if you are not asking question, okay? So for concave, different object positions would give you different images. So the next thing we are going to do is that we are going to use ray diagram to describe the nature of image formed when object is placed at different positions. So this is the pole. So I'm going to draw the principal axis. Now, we don't draw mirrors, okay, with a very large aperture. But what we do is that, I said practically, or the real life situation, mirrors used in the lab have very small aperture. So you don't draw a mirror like this, no. But what you do is that small aperture, then you rule a vertical line behind the mirror so that it caters for reflections that goes beyond the aperture of the mirror. So I draw something curvy small and then rule this vertical line behind it to cater for reflections that go beyond the aperture of the mirror. But you don't need to draw a bigger mirror, okay? Then, because I'm not giving any measurements, I'm picking a value for focal length and radius of curvature. So I'm using 10 centimeter. So I'm measurements are taken from the pole. So from the pole, I'm taking 10 centimeter. So you can also choose any other value, but the most important thing is that, so this becomes my F. My focal length is 10 centimeters. I am assuming if this is 10, then the center of curvature from the pole must also be 20. So carefully measure this. So this must be C. To satisfy R is equal to 2F. Okay. Now, any distance beyond the point C, any distance beyond the point C, it means that we are looking at the distance between infinity and C. Infinity is an infinite distance. So any distance beyond C, if you put an object, then it means the object is between infinity and C. So let's place the object either beyond C or between infinity and the point C. So objects between infinity and C, or this position can also be described as beyond C, as some students often call it beyond C. So I'm placing the object between infinity and C. Not a very tall object, just okay. So this is the object. It is beyond C or between C and infinity. We are going to use the rules. We are going to use the rules to form the image. And you need just two of the rules to form an image. So see how I'm going to apply the rules in a ray of light. The rays are always coming from the object. So you need to trace the incident ray to the object. A ray of light from the object going parallel to the principal axis. After reflection, what must happen? When the ray is parallel to the principal axis, after reflection, what happens? Class, if the ray is parallel to the principal axis after reflection, what happens? Anybody can answer. Don't waste time, please. Au revoir.
Yes, it should pass through F.
So the reflected ray passes through the principal focus or the focal point. If I use the terms, okay?
Yes.
So after reflection, the reflected ray passes through F. I need another rule. I need another rule. And there are several of them. You have a ray hitting the mirror at 90 will pass through C. You have a ray from the object passing through F after reflection. There are several of them. And you also have a ray of light hitting the pole. Any of this can work. So if I'm using a ray of light hitting the mirror at 90, then it means it must pass through C. As I said, we rule a vertical line to cater for reflections that go beyond the aperture of the. So if it is not hitting, just extend your vertical line. You are good to go. So what it means is that this rule, the ray would incident and reflect along the same path. Now, an image is formed whenever two or more reflected rays actually intersect or appear to intersect. So look at the reflection of this. This is it. Look at the reflection of this. These two reflected rays appear to intersect here. That is where the image will be formed. The point of intersection of the rays will be the head of the image. The foot of the object and the image is always on the principal axis. This becomes the image. So when you compare the object O to this image will come there. But I want to change the rule. I want to change the rule. Here we use a ray of light parallel to the principal axis after reflection passes through F, and a ray of light hitting the pole at 90 passes through C. I want to change the rule to see the nature of the image we'll have, so that we will not be repeating only two rules. There are several rules we can use. I can also decide to use this, a ray of light from the object. The rays always from the object. From the object passing through F. After reflection, what must happen? If the ray is passing through F, after reflection, what must happen?
It must be parallel to the principal axis.
So the reflected ray must be parallel to the principal axis. Yeah, when you have to be careful. Get your parallel thing well. Then I can also use a ray of light hitting the pole just to vary the rules. And once it is hitting the pole, it must reflect at the same axis. This angle you need to measure or estimate very well. I'm just estimating, so I just need to estimate right. Or measure well. So these two reflected rays, which is this one and this one, they actually meet at this point. This point where they meet is the object, is the image. So I've just varied the rules. Okay. Now let's describe this image. Let's describe the image formed. What would you say about the image formed? Yes. Compare the objects to the image. What do you have to say about the image formed? The nature of the image. Yes, Mamiya. One object, images.
It is inverted.
Exactly. Look at the object orientation and then the image orientation. So image is inverted. Let me change my earpiece. Okay. The battery is down. So let me connect a speaker rather. Give me some minutes to quickly do that. Okay, I'm coming up, please. Hello? Hello? Can you hear me?
Yes, please.
Hello.
Hi.
Please, I'm coming. Hello.
Hi.
I'm
No.
coming. All right, ma'am. Millicent, go ahead. Millicent. Millicent, your hand is up. Go ahead. Oh, the network. Millicent, your line is breaking, so come again, okay?
Diminished. Yes,
Okay.
sir.
All right. So when
Image.
I can hear you. I can hear you now. So when you compare the objects to the image, Millicent is saying that yes, object size is diminished. It's true. Sorry, image size is diminished, meaning the size is reduced. 3. So image is inverted, diminished. Yes. We are describing the nature of the image formed. What else have you seen? Elizabeth.
Please, I see that the image is below the object.
And the reason for which we are saying that it is inverted, the
Okay.
orientation isn't the same. Now, under spherical mirrors or mirrors generally, when an image is formed in front of the mirror, it is real. When it is formed, okay, behind the mirror or at the opposite side of the object, it is virtual. So you can clearly see that this image is formed in front of the mirror, and so it is real. Now, all real images are inverted. So that's why if the image is inverted, then it's real. Or if the image is real, then it's inverted. Okay. And then lastly, you need to talk of where the image is formed. This image is formed between C and F. So image or formed between C and F. This is a description of the image form when the object is placed between infinity and C or placed beyond C. Any question? Any question? Okay. Then let's place the object at C. Let's place the object at C and use ray diagram to describe the nature of the image formed. I'm going to do this with you. Then subsequent positions will be given to you to try. So measure F and then measure, I'm using the same thing. So 10 centimeter. So this is F. This is C. The object is at C. So use the rules. A ray of light parallel to the principal axis after reflection must pass through F. Oh, reflected ray. So after reflection, the reflected ray must pass through F. Vero, passes through F. Then a ray of light using any, you are free to use, okay, any of them. A ray of light from the object passing through F after reflection must be parallel to the principal axis. And here you have to be careful. Measure your parallel ray very well. Because this position is such that image must be formed at the same position. So if you don't get your measurements right, you will miss the point where the image is formed. So this is where the two reflected rays are meeting. And that will be the position where the image will be formed. Now, as I said, this position is such that you need to take your measurement very well. And then your parallel rays and all that very well. Else, you'll miss the position. Because when the object is at C, the image must also be formed at C. So let's describe this image. Let's describe the nature of the image formed. Yes. One image is quick one. Plus, let's not waste time. The guys coming, Caleb, Cadmiel, and then the rest of you, Calvin, Leslie, Nana. Yes, Elizabeth. One image is
real.
Image is real. All real images are what? All real images are.
Sir, please, they are inverted.
Thank you. So if image is real, it will also be inverted. 3. Your line is breaking. Somebody should take over. Elizabeth again.
Please, object length is equal to image length.
Or size. So image size, object size, the same. Or length equals object size. 4. 4. Hey, class 4. The talk. As for the when you come to school, I'll beat you. Elizabeth,
Please, the image is formed at C.
thank you. Formed at C. So these are the 4 main descriptions of the nature of. So assignment, your assignment. Using ray diagrams, describe the nature of image formed when objects is at the following positions. So 1 between C and F. C and F. Then 2 between the pole and F. These are the 2 assignments I have for you. So you use a for please convex. Did I say convex? Concave mirror. On Friday, I'll handle the convex. Then you can pick it up from there. So using ray diagram, describe the nature of the image form when object is positioned is at the following positions between C and F. So object must be here. Between the pole and F, object must be here. So in each situation, use the ray diagram, the rules as I've done, then describe the nature of the image that will be formed. This is your assignment. Okay, and the deadline for submission is you have to submit from today up to Thursday. Please, any question? Any question? All right. So if you don't have any question or suggestion, then this is where I draw the curtains on today's meeting. Thanks for your time. Thanks for your contribution. And then please take care of yourself. Until Friday, may the good Lord be with you. Bye-bye.
Thank you.
Bye.
Okay.